Let me tell you about something that has shaken the foundations of physics observations from the James Webb Space Telescope that have reignited a profound debate about the nature of gravity itself. What JWST has revealed about the behavior of galaxies, the distribution of matter, and the structure of the cosmos has led some physicists to propose something that sounds impossible, that gravity, as we understand it, may not be a fundamental force at all. Everything floats for a reason. This phrase captures a radical idea that has been gaining traction in theoretical physics. We do not fall because gravity pulls us down. We do not orbit the sun because an invisible force tugs us in circles. We do not see galaxies clustering because of gravitational attraction between distant masses. Instead, something far stranger is happening, something that makes gravity not a force but an illusion, not a fundamental feature of reality, but an emergent phenomenon, not the cause of motion, but the name we give to patterns we do not fully understand. I want to take you through what JWST has observed that has reinvigorated this debate, because understanding these findings requires appreciating both the history of our understanding of gravity and the revolutionary ideas that may replace it. Let me start with what we thought we knew about gravity. Gravity is the most familiar force. We experience it constantly in the weight of objects, in the arc of thrown balls, in the tides of oceans, in the orbits of planets. Gravity is what keeps our feet on the ground, what holds the atmosphere to the Earth, what prevents the moon from drifting away into space. Isaac Newton formalized our understanding of gravity in the 17th century. In his Principia Mathematica, Newton proposed that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple law explained the motion of planets, the fall of apples, the behavior of projectiles. It unified celestial and terrestrial mechanics, showing that the same force that governs the heavens governs the earth. Newton's theory was spectacularly successful. It predicted the orbits of planets with extraordinary precision. It enabled the discovery of Neptune, a planet whose existence was inferred from gravitational perturbations before it was ever seen. It formed the foundation of physics for over 2 centuries. But Newton himself was troubled by his theory. Gravity, in his formulation, acts instantaneously across empty space. The sun attracts the Earth right now, not after a delay for the influence to travel. This action at a distance seemed almost magical, and Newton famously wrote that he would not feign hypotheses about how it worked. The mathematics was clear, the mechanism was mysterious. Einstein resolved this mystery, or so we thought. In 1915, Einstein published his general theory of relativity, which revolutionized our understanding of gravity. In Einstein's formulation, gravity is not a force at all. It is the curvature of space-time. Massive objects do not reach out and pull other objects toward them. Instead, they curve the fabric of space-time around them. Other objects then move along the straightest possible paths through this curved space-time paths called geodesics. What we perceive as gravitational attraction is actually the natural motion of objects through curved geometry. This is a profound reconceptualization. In Newton's theory, space is flat, time is absolute, and gravity is a force. In Einstein's theory, space and time are unified into a dynamic 4-dimensional fabric that bends and warps in response to mass and energy. There is no gravitational force. There is only curved space-time and objects following its contours. Einstein's theory made predictions that differed from Newton's. It predicted that light would bend around massive objects, confirmed during the 1919 solar eclipse. It predicted that time would slow in strong gravitational fields confirmed by countless experiments since. It predicted gravitational waves, ripples in space-time caused by accelerating masses confirmed by LIGO in 2015. General relativity has passed every experimental test we have devised. It is one of the most precisely confirmed theories in the history of physics. It forms the foundation of modern cosmology, describing the expansion of the universe, the formation of black holes, the evolution of cosmic structure. And yet, some physicists now argue that even Einstein's theory does not capture the true nature of gravity. They argue that gravity is not fundamental but emergent, not a basic feature of reality, but a consequence of something deeper, something more fundamental, something we are only beginning to understand. Now let me describe the emergence of emergent gravity. The idea that gravity might be emergent, arising from more fundamental physics, has roots going back decades. But it has gained new momentum in recent years, driven by developments in theoretical physics and, most recently, by observations from JWST that challenge our standard models. What does it mean for gravity to be emergent? Consider temperature. Temperature is not a fundamental property of individual atoms. A single atom does not have a temperature. Only collections of atoms do. Temperature emerges from the collective behavior of many particles, from their average kinetic energy, from the statistical distribution of their motions. Temperature is real, measurable, consequential, but it is not fundamental. It emerges from something deeper. Similarly, pressure emerges from the collective impacts of molecules on a surface. Fluid dynamics emerges from the microscopic motions of particles. Thermodynamics emerges from statistical mechanics. Many macroscopic phenomena that seem fundamental turn out to be emergent, to arise from underlying microphysics that does not obviously contain them. Could gravity be like this? The idea was first seriously proposed by Ted Jacobson in 1995. Jacobson showed that Einstein's equations of general relativity could be derived from thermodynamic principles, from considerations of entropy and temperature applied to horizons in space-time. This was remarkable. The equations that describe the curvature of space-time, traditionally derived from geometric principles, could also be derived from thermodynamic principles. This suggested that gravity might be thermodynamic in nature, that it might emerge from the statistical behavior of underlying microscopic degrees of freedom, just as temperature and pressure emerge from molecular motions. Erik Verlinde, a Dutch theoretical physicist, developed this idea further. In 2010, Verlinde proposed that gravity is an entropic force, a force that arises from the tendency of systems to increase their entropy. In this view, objects do not fall because of gravitational attraction. They fall because falling increases the entropy of the universe. Verlinde's proposal was controversial but influential. It suggested that gravity is not fundamental but emergent. Not a force, but an entropic effect, not built into the fabric of reality, but arising from information and thermodynamics. More recently, Verlinde has extended his ideas to address the dark matter problem. In his emergent gravity framework, what we attribute to dark matter might actually be an effect of gravity behaving differently than general relativity predicts, not because of invisible matter, but because gravity itself is modified at large scales. Now let me describe what JWST has observed that bears on this debate. The James Webb Space Telescope has observed galaxies at unprecedented distances and with unprecedented precision. Its infrared capabilities allow it to see through dust, to observe the earliest galaxies, to measure the motions and masses of cosmic structures with extraordinary accuracy. Several of JWST's observations have proved difficult to reconcile with standard cosmological models, models that assume general relativity plus dark matter plus dark energy. First, JWST has observed galaxies at very high redshifts, very early cosmic times that appear more massive and more evolved than standard models predict. These impossible early galaxies seem to have formed too quickly, to have assembled too much mass, to have developed too much structure in the time available. Standard cosmology predicts a gradual buildup of structure, with small galaxies forming first and larger galaxies assembling later through mergers. JWST has observed galaxies that challenge this timeline, galaxies that are too big, too bright, too mature for their cosmic epoch. This could indicate problems with our understanding of galaxy formation. Perhaps stars formed more efficiently in the early universe. Perhaps feedback processes were different. Perhaps our models of baryonic physics are incomplete. But it could also indicate problems with gravity itself. If gravity behaves differently at large scales or at early times, this could affect how quickly structures form, how efficiently matter clusters, how galaxies assemble. Second, JWST has observed the rotation curves of distant galaxies with unprecedented precision. Rotation curves graphs showing how fast stars orbit at different distances from the galactic center are the classic evidence for dark matter. Stars in the outer regions of galaxies orbit faster than they should based on the visible matter. Dark matter supposedly provides the additional gravity. JWST's observations have confirmed that rotation curves remain flat out to large radii, consistent with dark matter. But they have also revealed subtle features, bumps and wiggles in the rotation curves that do not match standard dark matter models as well as expected. These features might be explained by the complex distribution of dark matter in galactic halos, but they might also be explained by modified gravity, by gravity behaving differently than general relativity predicts without the need for dark matter at all. Third, JWST has observed gravitational lensing, the bending of light by massive objects, in unprecedented detail. Gravitational lensing is a direct probe of gravity, revealing how mass curves space-time and deflects light paths. The lensing observations have been broadly consistent with general relativity, but they have also revealed anomalies, discrepancies between the lensing predicted by visible matter and the lensing actually observed. Standard cosmology attributes these discrepancies to dark matter, but they could also arise from modified gravity. Fourth, JWST has contributed to measurements of the Hubble constant, the rate at which the universe is expanding. The Hubble tension, the discrepancy between early universe and late universe measurements of the Hubble constant, has persisted despite JWST's observations. This tension might indicate systematic errors in measurements, but it might also indicate new physics, perhaps modifications to gravity, that affect cosmic expansion differently at different epochs. These observations do not prove that gravity is emergent or that general relativity is wrong, but they have created tensions with standard models that have led some physicists to consider alternatives, including the possibility that gravity is not what we thought it was. Now let me describe the theoretical framework that suggests gravity is not real. When physicists say gravity isn't real, they do not mean that apples